Perfect. Cao Zhang Hao, Xie Daja. Thank you for coming to my talk today. I am very excited to dive into the state of production machine learning in 2019. The slides are in this link on the top left of the presentation. You can access it. Hopefully you can access it. Okay, he says you can't access it. So if you want to access it, you go to github.com ethicalml, and then you'll be able to see the presentation called State of MLOps 2019. So thank you for the heads up. That is the link. You guys can access it. The slides are going to be there. And the links to all of the examples that we will be using will also be there. So, let's zoom in. Yep, good idea. Oh, right. Oh, can we remove the... Perfect, thank you for the heads up. All right, so if you just go State of MLOps, I think you can see it there. Let's get started. All right, so thank you again. We're going to dive into the state of production machine learning in 2019. My name is Alejandro Saucedo. You can find my Twitter down there. I am the chief scientist at the Institute for Ethical AI and Machine Learning, and I'm also the engineering director at this open source company called Seldon Technologies. The Institute is a research center that focuses on building standards for the use of machine learning in production. And Seldon is an open source machine learning deployment and orchestration platform that allows you to deploy your models from research to production. And you can check out and try out the platform with Seldon on seldon.io. So let's talk about data science projects. So small data science projects, in essence, they are not a big problem. So you tend to have two workflows. The first one is model development, and the second one is serving your developed model. It consists of the usual steps of getting some data and cleaning it, defining some features to transform the data, selecting a model, defining scoring metrics, and then iterating. Once you're happy, you persist that model, and then it goes to production to be able to serve any inference data that you see coming through, right? So in small projects, it works relatively well. However, as our data science requirements grow, we face new issues. Increasing complexities of flow of data. So who here has used crontab? Let's see a show of hands. Yes, so people may know what crontab nightmare looks like when you scale too much without the process around it. Each data scientist has their own set of tools. Some like TensorFlow, R, Spark, and good luck taking that away when it's actually a very productive tool. Serving models becomes increasingly harder as there's a larger number of them in production. There's more high parameters in place, there's different versions of each model running with different trained data, etc., etc. And when stuff goes wrong, it's hard to trace back. Not only in terms of the people that are involved, but also the responsibility that is laid. So how do you manage whose person needs to be in charge of what? And then as your technical function grows, also should your infrastructure. And that is where the concept of machine learning operations comes in. So it is this layer of complexity that is not just product or features, it's also processes and best practices. And it is challenging. The role of machine learning engineering is still being defined. It is the intersection of software engineering, data science, DevOps, etc. And not only that, but when you see a job description for a machine learning engineer, it tends to be something like, we need a professional with a PhD, 5 years experience software development, experience with DevOps tools like Jenkins, data science experience to build models, consultant experience to figure out where to apply them, so a McKinsey consultant for a salary of an intern, right? That's what you tend to see in this sort of stuff. So it is currently being defined because it's a spectrum, and we're going to cover some of that. And we've also mapped the ecosystem. We have another link that cannot be reached, but it's still in the same repo, github.com/ethicalml. This has one of the largest and longest tool set to be able to find frameworks to manage your production machine learning. If you see a tool that you can't see there, please feel free to contribute. The principles that we're going to cover today, however, are the principles of reproducibility, orchestration, and explainability. So let's get started with reproducibility. Reproducibility encompasses the concepts of model and data versioning. So being able to keep track of your models as they're in production, but also in development as you train them. This requires an abstraction of the individual steps into atomic, self-sustaining, and versioned models. And it includes the data that comes in, the code/configuration, and the data that comes out. And this is complex, not only because you already have the challenge of keeping track of these three different concepts, but also that it goes one level higher into the definition of your computational pipeline. And you may have some feature generators, you may have some models, some data cleaners that you may want to use and reuse, right? So you need to keep track of what is inside, but how it all stitches together, and version that in some cases as well. So what we're going to dive now into is a case study, an example of reusable pipelines in an NLP use case. So we're going to be using this technology that we're contributing to. You can also access it through this link, or it's on the Git repo, which we're going to link. But this is basically what Kubeflow is. It allows you to define computational pipelines of your machine learning. And the interesting thing about this is that we have reusable steps of an NLP pipeline. What you see here is an NLP classifier. It basically takes a sentence and it states whether it should be moderated or not. It's hateful speech or not. And this is basically something that is done in forums. We took the Reddit hate speech dataset, which is basically the dataset that moderators was collected from moderators that removed comments. And what we show here is we have a continuous stream of tweets. And these tweets are the Brexit tweets. I don't know if you're familiar with Brexit in the UK, but it's basically processing all of Brexit. And what we're going to do here is we're going to train another pipeline where the last step is a deployment using Seldon. So we're using Kubeflow to run the downloading of the data, the cleaning of the text, the tokenization, the vectorization, the prediction, etc. So here you can see also in the logs, the input and output. I think the tokenizer shows it a bit better. So here you can see the string and the tokens coming out, right? So you can see through the UI an ability to train pipelines. So we're going to go here. We're going to select the pipeline that we defined programmatically. And we're going to create a trigger. So this is going to be run number 4. Here we can define some hyperparameters. In this case, we're giving our data set for the GitHub comments, but we can also have a Twitter data set of sentiment analysis. So as long as you pass a CSV file together with, the name of the column where you have the features, the text, and the name of the labels that you're going to use to train your model. Right? You can also pass things like the number of TF-IDF vectors, the n-gram range, and some hyperparameters for the different steps. And then we can actually just trigger it from the front end. We can just basically see the running pipeline in real time. So this is actually running in my local machine. And as you know, we don't have the best internet in this place at this point, so it's going to probably take a while. The first step, what it did is it created a persistent volume claim, and it's going to attach it to every single container so that the containers can use that volume to pass the data from one to the other step, And this is interesting because there's full provenance of the data that is currently available. And what that means is that every single run, the inputs and outputs of every single one of those steps is actually stored in a persistent volume that then can be backed up, right? And then the internet right now, it's like connection refused. So I probably need, the VPN. But I actually have it like running on an online cluster that I'm going to show you because I was preparing for this just in case. And I'm actually going to also connect to my server just in case as well. So basically what you're doing here is you're training a pipeline, and the end result will be basically a run that you're storing with the respective persistent volume. So in this case, it downloads the data, it cleans it, etc., and everything is stored in this persistent volume with the ultimate goal of deploying it into your Kubernetes cluster. So that is the whole essence of these multiple steps that are involved there. And there are also several other tools that you can use for the reproducibility of your machine learning, such as this tool called data version control. This is a GitHub, Git-like fork that also allows you to take to save state of all of the different components, the image, the data, the code, and the inputs and outputs, etc. So the way that you interact with it is very similar to the way that you interact with Git. And they have a very, very interesting approach. MLflow is another tool from Databricks. They have an approach to manage your experiments and track your experiments. And then finally, we have another tool called Pachyderm. Pachyderm focuses on fully reproducible pipelines. So there is actually a very interesting integration that we do with Pachyderm as well. And that is for the piece of reproducibility. This is an interesting concept because all the different parts of the grid that you saw, I could dive for 2 hours and talk about them, right? So they are quite complex. But the important thing from this talk is to get a feel of the ecosystem and to more than anything, just get involved and help the conversation, help us push the conversation forward. Now, the second part is on model orchestration. This involves training and serving models at scale. And this is basically what we do primarily at Seldon. We have an open source framework that allows you to containerize language agnostic models. This can be Python, of course, but also can be Java, R. If you're feeling like a cowboy, you can also do Fortran. I mean, if you build a wrapper for it, I don't know why you would, but you also can encapsulate legacy models. And this involves also about serving at scale. So it's not just about the complexity of putting the models in production, but it's about also orchestrating them, standardizing the metrics. And we're going to talk about that stuff. So, and this is a hard problem because it becomes a computational resource allocation, right? It's services with different computational requirements, with often complex computational graphs. We need to allocate the right resources at the right time to also not overshoot, right? And this is a hard problem. But fortunately, we have managed to leverage a lot of the Kubernetes infrastructure. And with the relatively recent debut of CRDs for the last 2 years, we're also able to abstract some of these complex concepts of infrastructure and being able to define them in encapsulated components. So then we can suggest design patterns in the same way that you would in object-oriented programming, right? And we're going to actually cover some object-oriented design patterns for your infrastructure as we discuss this. And the reason why also serving and deployment of models is hard is because it introduces a layer of governance and compliance. So that already ambiguous field of machine learning engineering that we touched upon is in the intersection with other industry-specific fields like policy, expertise, industry domain experts, and then that forms the centerpiece, which is the question of what are the standards? What are the key processes, metrics, frameworks, risk assessment processes that we can have in place to make sure that we have our production machine learning following the right policies, etc., etc. And we're actually contributing to several standards with IEEE and several of the other bodies like ISO to define standards like the algorithmic bias standard. And in order for us to be able to go one level higher, we need to define the standardization of metrics, right? We've done this for microservices. We know that latency is something that you would track. We know that requests per second, errors. But when it comes to models, you have other metrics that you may have to standardize, like accuracy, precision, recall, model divergence, et cetera, et cetera. And what is interesting from there is that then is mapping those metrics with your internal policies to create this concept we call programmatic governance, right? Not only you define your policies, with actual writing, but you're able to also encode them in your encode them through your infrastructure, right? And in this case, what we provide is standardized metrics with any model that you deploy in production. But we are currently working with the Kubeflow team, and this is a very interesting initiative to create some standard for those metrics that are going to be exposed, so that any model that is deployed in production is not always going to have them, but we can all have at least an agreement that at least it should. And that is an important thing. The second piece is also standardization of errors and logging, right? Right now, a lot of the times, it is data scientists having to maintain their models in production. But with the introduction of these tools, you're able to create a division so that there is a distribution of responsibilities. Data scientists do data science, sysadmins do sysadmin, right? And you can also then go into higher level tasks like complex deployment strategies. So with Seldon, you can do things like explanations, outlier detection, feature transformations, etc. But this is about defining your computational graph specific to machine learning, right? So this is not new and super cutting edge in terms of the higher level, but what is new is being able to abstract it into machine learning. Abstracting infrastructure into machine learning. And then is introducing GitOps. So we're going to dive into this example. Has anyone here heard of this new platform called PyTorch Hub or TensorFlow Hub? Let's see a show of hands. PyTorch Hub, TensorFlow Hub. Okay, cool. So basically what that is a repository where researchers and engineers, they can actually submit their trained models. Things like BERT, GP2, things like VGG, all of those neural networks and models that were trained on massive scale data, or just models that you've trained, can be actually just put in GitHub and made available. So you have that way of versioning that we discussed previously with your code and model and configuration, right? So what we do is we're able to provide an integration, and this is all open source, by the way. This is all open source. We're going to show all of the examples are available online. We're able to have a direct integration, GitOps integration with the PyTorch Hub GitHub. And what GitOps is, it basically means you keep in sync your GitHub definition and your production environment. So if something changes in GitHub, something changes in your production, right? And that is sort of your layer of quality that you make sure that there's an approval process around that. And in this case, we provide that GitOps layer between PyTorch. Whenever a new change comes in, then the Seldon gets triggered, it wraps and containerizes the model, and then the model is put into production. It could be like, a simple model, it could be, an A/B test, it could be a stacked set of models, etc., etc. And then we're going to dive into that example. So basically, the first example was here. You can actually build your NLP pipeline. You can try it out yourself. But now we're going to dive into the next example, which is building production level PyTorch Hub models in Kubernetes with 10 lines of code for it to look like that. The ultimate objective is to separate concerns, right? Your data scientist is able to use the models. Your SRE, DevOps person is able to manage them and monitor them, right? That's the main thing, is how to abstract and distribute concerns and separate concern. So let's actually zoom in. So the process, the steps that you would do is you would basically first just create a wrapper, in this case for Python, of your model. Create a wrapper of your model that has a predict function. So anything that takes an input and returns an output can be wrapped. In this case, we can take NumPy arrays, but we choose to take the highly optimized tensor through the byte serialization, right? So what this does is a wrapper that takes some tensor, runs it through the loaded model, and returns the inference result, right? It just so happens that when it's initialized, it calls torch.hub.load, and it loads the specific model, right? So what this basically does is it's a wrapper for PyTorch Hub that is able to load models dynamically from PyTorch Hub. And once it's in production, when you send any requests, it's going to basically be able to, run everything to that model. So what we would do is we would just save this in a file. So we're doing write file in deployment image, PyTorch, Seldon deployment.py. Then we specify the requirements of that, code, of that Python code. This requires PyTorch, NumPy, the image pill library. And then we create a configuration library that says what's the name of the model that the name of our wrapper class. And then we just use the S2I tool to be able to build it. This basically containerizes it and builds a Docker container that has a REST API and a gRPC API together with Prometheus metrics containerized with that wrapper. So now if we spin up that container, if we pass the model that we want, it would basically dynamically pull that model from PyTorch Hub, right? So we basically created our Seldon configuration, and every time that we trigger it, we just say, I want ImageNet or Inception B3, and it just basically pulls it and deploys it into Kubernetes, right? So in this case, we define our, like a YAML file that specifies that image that we just built. So is that containerized PyTorch wrapper. And the only difference is that here we have a replacer for the parameters that we pass. So this is our own Seldon definition, right? So you define the containers, and then you define the computational graph, right? In this case, it's just a computational graph of one node. And we're passing the parameter model name, which in this case would be, VGG 11 or VGG 19, or it can be BERT, right? Whatever it is. And what then it does, it basically deploys it. So here we're just actually doing a sed replace. So we're deploying the mobile net. And then when you actually run it, you can see that it's actually running because we pass those parameters. It's called PyTorch Hub mobile net, right? MNet. And we can actually get the logs to see that it actually downloads it and then runs the application. And then we can just send REST requests, right? So we create a Seldon REST client, but you can also do curl or Postman or whatever. And we load an image. So this is the image of this dog. We convert that image into tensors, and we send the bytes of those tensors for getting like that request and response, right? So we import pickle, and then we just send the predict. And then similarly here, we're unpickling the response, right? So it's sending the request, and then we get the response. So it's basically a REST API, a gRPC and REST API that you've deployed, and now you can interact with, right? So ultimately, you build your model in Python, you build a wrapper, and then you're able to just deploy it as many times as you want. You can have your replica scales, etc., etc. So you get all the benefits that Kubernetes gives you. And again, this example is online, so you can actually jump in and try it out. So that is for that. So again, check it out. That's going to be on this. And again, for the people that just arrived, is github.com/ethicalml, and then you'll see State of Machine Learning 2019 that you'll find that link. And then other libraries to watch, because this is a whole ecosystem. You'll find this in the list. MLeap serving focuses on optimized serving of models. This allows you to use serialized definitions like PYMML, as well as several other standards, ONNX, that you can actually use for the deployment of your models. Deep Detect is a unified API that abstracts some of the most common libraries. And these are different sort of levels of abstraction, right? Like these ones focus primarily on unified libraries, so they don't really containerize. So it really depends on the use case. We try to focus on a more higher level generic use case. And now we're going to jump on the third part on explainability. So this is basically tackling the issue of black box model situations. And the reason why this is important is because in highly regulated sectors, if you're predicting someone's approval of a loan, whether someone's loan should be approved or rejected, if there's a regulation in place, like you need to be able to explain why a prediction ended up being in a certain way. For various reasons, perhaps whether it is discrimination of a specific group, whether it is a bias, inherent or unconscious, conscious or unconscious, whatever is the underlying reason, explainability is a very important piece into machine learning. And explainability needs to go beyond the algorithms. It is important to find the tools, but it's also more important to identify the process. And the process that we currently follow, it extends the traditional data science workflow by introducing 3 steps. So data analysis, model evaluation, and production monitoring. And for the data assessment, the first part, it's identifying things like class imbalances, protected features, things like correlations, data representability. All those things are very important to be able to identify, but also to match with the specific domain. For the model assessment, and we're going to dive into that, is feature importance, local versus global methods, black box versus white box model explanation methods, model metrics analysis. In this case, that is a feature importance, permutation feature importance approach. And then the last one is production monitoring. This is the question of what are the metrics that you need to put in place in order for your production environment to have a reasonable level of monitoring and alerts even perhaps, right? If there's a model divergence, what does that even mean? Because of course, accuracy, it is context specific, right? Like you can't just arrive and 90% accuracy in one use case is different to another. And the reason why this is important is because when now going into production deployment of machine learning, you now encounter things like SLAs that you need to abide by, right? With microservices, it's easy, right? Uptime, you may have sometimes support, et cetera, But with machine learning systems, there may be some metrics that need to be defined in place for that to reflect what value is being brought. This could be things like accuracy. This could be things like precision, recall, et cetera, level of explainability. What would that even mean, et cetera. And what we're going to be diving into is something, a very interesting piece, is going on the higher level part of this, leveraging Kubernetes, and more specifically, as I mentioned previously, the CRDs within Kubernetes. Leveraging this has allowed us to provide a higher level of abstraction for design patterns in machine learning. In this example specifically, we have a design pattern which I call the explainer pattern. In this case, you're able to deploy a machine learning model, which could be a black box model, a containerized model, as we just showed. This could be like a PyTorch model, like BERT or VGG or whatever it is. And then you would deploy sort of like a respective explainer, right? And this explainer would be able to explain why the model is doing the predictions it's doing, right? So whilst you would have a model doing predictions, you would have another model explaining that model's predictions. And that sounds really meta, right? that sounds like Inception, but it actually is more practical than you think. And we're going to be diving into an example for this last part. We're going to be using this library that we open sourced called Alibi. So this is basically a model, black box model explanation library. And we're going to be using specifically this concept of anchor model explanations. So this basically asks the question, if the model made a prediction, what pieces of that input, what were the features that made that prediction that label? In this case, is the question of what made this picture a cat, and it identifies what are the pixels that have most predictive power for that specific prediction, right? So this allows for explanations of the model itself, and we're going to be using that in our example, right? So in this example, we're going to be basically first building a income prediction classifier, right? So we're going to run first all of our components with Helm. Then we're going to train a model using the income classifier dataset. So this is a tabular dataset to be able to predict whether somebody earns more or less than 50K. We will have then a model that is basically trained on that. So we're using just basically a label encoder to be able to process the data. We're going to create our preprocessor, and then we're going to create with a random forest classifier the predictor, right? So we basically just have a model, right? We have a model. We're going to treat that as a black box model. It doesn't matter if it's a neural network, a random forests. We don't care, right? It's a black box model. When we run a prediction, so we can see that the performance, and it's going to predict either a binary positive or negative class. And now we're going to containerize and deploy the model. So again, we create a wrapper. So this wrapper basically just loads that pickled model that we just created. And whenever you call this function, it takes whatever the input is, runs it through the model, and then returns it. So this is going to be our API, right? So once you create the wrapper, we basically define the dependencies again and build a container by just pointing to that wrapper. And now we have a containerized model. We deploy it to Kubernetes with the same definition, with kubectl apply. So we're just saying that container we just built, we want a REST API for that. And then once it's in production, we can actually just send curl requests. So here we're sending the data for that income classifier. So these are the features. And then, we get the prediction here, whether it's positive or negative. So here it was, a negative prediction, right? So what we now do is we actually take one of the explainers, the anchor explainers, and we basically take that explainer and use that function of the model. So we basically give the model to be able to say, well, what from that model gave that prediction? And in this case, it says, well, it was marital status being separated, and sex female, what made that prediction being rejected, right? So that's what it basically does. But the cool thing is that we can now connect through, that same, we create a function that reaches to that model we deployed, right? And we now can actually make that explainer point to the production model, right? So we're basically now, instead of explaining our local model, we're explaining that model in Kubernetes, right? So we're basically just saying, well, use this this remote function, predict remote function, which is just sending the request there, and we can actually explain that remote predictor. So now that we can actually explain the remote predictor, we can deploy our explainer, right? And we follow the same steps. We are going to containerize it by creating a wrapper, right? So we just create a wrapper, we containerize it with our script, and then we push it to production. So we containerize it and we push it to production. And now we basically have, as I explained, a model to be able to run predictions, and then a model to be able to explain the predictions that it ran. And we actually have a front end that we can use to actually show you how those predictions would look like. So here we have the income classifier. We can see all the logs, so all of the predictions that have gone through that model. And we can actually request, if internet's on our side, we can actually request the explanation for that specific prediction, right? So here we can see why it predicted what it predicted. So it's the same thing we saw, but shiny, right? So right now it allows you to just see what we saw. So now it's cool. Before it wasn't cool, but now you can see what power it has. So just to wrap up, because this is the last few slides, there are other very cool frameworks like LE5, Explain Like I'm 5, SHAP, which I would recommend to check out, and XAI, which focuses more on that data. So with that said, we covered a high-level overview of the ecosystem. There's still so much more to cover. Please go check out the ecosystem list. This is one of the most extensive lists of open source tools on production machine learning. Please contribute because we want to have a more embedded understanding. We've just added this week a new section on adversarial robustness, which is really cool. And we're going to actually add that to the production set of toolset. So with that said, thank you very much. You can find the slides online. If you have any questions, I'm going to stick around. So thank you very much for your time.